So, hello. In this presentation, we're going to explore the crucial role of TCP packets. And let me think. No, this one. So the crucial role of TCP packets, and we'll also see how even a single TCP packet can cause disruption in very large firewall data centers. To illustrate this behavior, we'll go over a use case we had at TomTom. We will see how we identified the issue using TCP captures. And we'll finally talk about what you should monitor to avoid these kind of challenges in your infrastructure. Small disclaimer, this presentation will not contain any AI-related stuff. So in this regard, it's pretty old school, I would say. Before starting, a bit about myself. I've been coding for more than 15 years, and I'm currently a staff engineer at TomTom. In my free time, I like DIY projects, home automations, and building model airplanes. I promise you this one did fly for about 3 meters before it dived headfirst into the ground. I also built this with my daughter. This actually stood the test of time, so it's actually working after a couple of years. Unlike this car, which, well, didn't make it past its first week. So one more thing about me. So in 2015, I was at Go to Berlin, and I watched a talk by Russ Olsen, which is called To the Moon. So in that talk, I learned how to never back down from doing hard things. And this presentation will be about the hard thing that we did at TomTom. So I invite you to go to see the To the Moon by Russ Olsen. At TomTom, I am part of the Access Management Service team, which serves as a gateway to a lot of TomTom services, like routing, search, navigation, maps, and others. To give you an example, in here you see a navigation on the car display. This means that from time to time, there will be calls made to the TomTom services in the backend to gather data related to the route you're taking. This data can be various, like map layers, waypoints, and metadata about different things on the map. Before these requests can be made, like you see here, a couple of things need to happen. So let's see what are these. The first call goes to the Access Management Service team service when you start your car, so you don't need to do anything for this. This happens without any user intervention, which is a logon call. From this call will result a session token, which will be valid for a duration, let's say 2 hours. And with this session token, the car can call the backend services in TomTom. Second step is for the car to check if the gateway service is available. And this check is done with a very simple call on the route path. The request is simple, so no payload, no certificate, no headers. And the reason for this is that sometimes cars have unreliable internet connection. So we don't want to spend precious bandwidth with simple checks. This is the call that we will discuss throughout the presentation, and almost all the investigation that we've done revolved around this call. So keep this in mind. At this point, the car has been logged in, and it also checked that the gateway service is available. The third step would be, let's say, normal calls to gather data points and waypoints and everything for the navigation. And in this call, the car will add as header the session token, which it obtained earlier, and then call the search API in this case. After the request gets to the gateway service, the gateway service verifies that the token session is valid, and it will forward the request to this search or routing. So until now, we saw that the AMS consists of 2 services, logon and gateway. But we didn't see how and where these services are deployed. We will discuss 2 setups, so on-prem and cloud deployments. But first I will go for the on-prem, and we'll see what cloud setup we wanted to achieve. A couple of years back, all our infrastructure was deployed on-prem using multiple VMs for each of the services. You can imagine that scaling, monitoring, and changing this infrastructure was difficult at best. And as you can guess, it was also expensive. To enhance our service reliability, scalability, and performance, we aimed to migrate to the cloud, and more specifically to Azure Cloud. Additionally, migrating to the cloud offered advantages such as simplified disaster recovery and cost reduction, which companies also like. Yeah. So as part of the cloud migration, we came up with the following architecture. So we had a very simple Azure load balancer. We have an Nginx ingress controller, which people with Kubernetes are very familiar with. And we had a Kubernetes cluster that would be able to dynamically scale our logon service and gateway service as needed. After creating the infrastructure, we deployed our services and ran regression and performance tests to make sure that the functional and non-functional requirements are still met. Since everything was working correctly, well, there was one more thing to do. Well, it's actually not deploy all the things, but just switch our DNS traffic to point to the new infrastructure so that the downtime for the clients, for the cars, would actually be very minimal. A couple of things that did happen after the switch. What do we all do? Like monitor the dashboards of Grafana for different things like HTTP requests, server metrics, Kubernetes state, right? Everything needs to be monitored. But actually, there was one more metric that we didn't know about. And I will talk about this metric at the end of the presentation. A couple of things that could have been better. So, if you don't have more requests or the same number of requests coming to the system, that means something has gone wrong somewhere. That somewhere we didn't know at that point. So, what do we all do in this scenario if it's not going good? Well, roll back. And again, it's not just it's not the rollback; it's just a DNS switch. So the cars would not even know that there was some other infrastructure. And now it would be time to make a plan, right? Anybody try to fix that bug that you fix one time and then comes up in the next sprint and in the next and triggers other bugs? This is kind of what we had to do. So a couple of things that we did try without success. Beefing up our infrastructure was one of them. Throw more VMs, maybe it works, I don't know. Adding more SNAT ports. So SNAT ports are used for making outbound connections. We thought that our cluster couldn't make enough outbound connections, so we said, okay, well, let's give it more SNAT ports. We also disabled our HTTP keep alive for our Nginx ingress. We thought maybe the Nginx was keeping the connections open, and that was not the case. So when all else failed, we tried a bit of a different approach. So this F5 was on-prem. We left it in place, so that means that the connection between the cars and the TomTom services would not have changed at all. But actually, the backend services would be deployed on the Azure Kubernetes service. And there it was. Everything was working properly. So that means at whatever the issue was, it had to be something with an F5 configuration, but this configuration would not exist in our Nginx, right? So after a lot of investigation, turns out that the F5 setting was SSL handshake timeout. That was set on F5, but Nginx does not have this one. So what this means is that if the handshake, the SSL or TLS handshake, is not completed in a certain duration, in our case it was like 5 seconds, F5 will send back a reset packet that will basically end the connection. Like I mentioned, Nginx does not have this setting. It does have SSL session timeout, but that is for a different purpose. So let's dig into the TCP land and see why this SSL handshake timeout is actually very important. Anybody seen this joke? Yeah, 1, 2, 5, yeah, okay. So TCP does rely on, has reliable communication, right? So a stream of data sent on a TCP connection is delivered reliably and in order at the destination. Some packets might be retransmitted, but that's part of the protocol. And yeah, so to establish this reliable connection, TCP uses a three-way handshake. This means that both parties need to syn and ACK each other. And earlier I was showing that the car needs to do a check to see that the gateway service is there. So let's see what happens and when a connection check is done from the car to the AMS service. So connection check starts at the car, and this is the how would the TCP packets would look like. And at the bottom you can see that there's a reset packet which signals the end of the request. And it's a bit rude for the car to end the connection like that, but it is valid according to the RFC, so it's okay. Then the packets go through a couple of network antennas. So the network provider has antennas all over, but one of the antennas delays a bit the delivery of the reset packet by a couple of microseconds, not much. These packets then arrive at the firewall. So the firewall has two sides, one inside, one outside. I will discuss about this later. Which does the inspection of the packets and decides that the reset packet, well, is not according to the specification, and it drops the packet. So on the outside of the firewall, you cannot see that reset packet anymore. Finally, the packets arrive at the AMS system without the reset, meaning that the AMS system does not know that the connection was actually closed by the car. So it thinks it's still opened. I will go over more details regarding this packet a bit later, but first let's see let's talk about the firewall overview and what functionality it did for us. The firewall has two sides, one inside and one outside. In our case, the purpose was to do TCP packet inspection, but also to translate the car private IP to a public IP. So all the cars, in this case client, had private IPs, and these IPs needed to be knotted to a public IP. The outbound connections of the firewall uses SNOT ports. The more SNOT ports you have, the more outbound connections the firewall can make. If a reset packet is seen on both sides of the firewall, like you see here, then the connection can be closed because both sides of the firewall know that the connection ended. If the connection is seen only on one side, like you notice here, then that particular SNOT port will be occupied for the duration of a connection timeout setting, which is set on the firewall. In this case, it was 1 hour. So keep in mind 1 hour, it's important. Now imagine that you have hundreds of thousands of translations going on. So meaning if you have hundreds of thousands of reset packets that are only on the inside, all those SNOT ports will be occupied. Let's see some TCP captures to better understand this behavior. And we'll start with the TCP capture on the device, right, on the car. So again, this is the call that the device makes to make sure that the gateway service is there. If it gets any response, including a certificate error, that means something is there and the service is up, according to the check. So the TCP captures would look something like this. And highlighted, you can see a particular packet, which is the reset packet sent from the device, which we saw earlier in the connection flow. Immediately as the server presents its certificate, I'm not sure if it's visible, but let me see. No, it's not visible. So the server presents its certificate, but then the device says, well, I don't know who you are, so I'm just ending the connection immediately. It's a bit rude, but it is valid according to the RFC. So now let's look at the TCP captures on the firewall using the two different infrastructures. So we had the F5 infrastructure, which was on-prem, and the Nginx infrastructure. And first, I will take a look at the F5. So if you see at the top right, it's the F5. And on the top left, you see before NAT, so before translation. So this is where the TCP packets are inspected, and if they're not correct, they will be dropped. And the TCP packets will need to come in certain order and have a certain sequence number assigned to them. So every packet that is allowed to move past this side of the firewall will have its private IP translated to a public IP. So highlighted, you see the reset packet sent from the device, which has the IP of 1234, which is the first one, right? The reset packet there. So at this point, you think, well, the connection should have ended, right? Because it's a reset packet. But actually, 5 seconds later, you can also see at the bottom, there is another reset packet. And this one is not sent by the device. It is sent by the AMS system. And in this case, by F5. So, of course, it's a bit strange. Why would you see two connection endings, one after the other? But now let's look a bit still on the firewall, but this time on the outside interface, meaning what packets were allowed through the inside. Oh, yeah, okay. So this is the capture after the translation, so the outside of the firewall, but this is the interface that communicates directly with the TomTom services. This is also sent to F5, right, like I mentioned. And all packets that are present on this interface will also arrive at the AMS system. One important thing to note is that we don't anymore have the reset packet from the device. So in this outside interface, the firewall doesn't know that the device ended the connection. But there is the reset packet coming from the AMS. So basically, the AMS, in this case F5, is saying after 5 seconds, hey car, I didn't hear anything from you, so I'm just ending this connection. So it's fine, and that this worked for a while, but then when we switch to our new infrastructure on Nginx, let's see what happened. So this is the same connection checker request. I removed a couple of the packets for brevity, but if you see on the right, we have Nginx. And this is still after network translation. In this case, we see that the packet from the device is also not there. But we can also observe that the Nginx does not send any reset packet. So why is that? It actually tries to end the connection in a nice way with ACK and FINAC, right? That's the proper way to end the connection nicely. But it will need confirmation that these packets were received by the firewall, right? Or by the car. But this confirmation, of course, never comes. So according to AMS, the connection is still open. But at some points, these retransmissions need to stop, right? And this is controlled by this property called TCP orphan retries, which by default is 8. You can see only 7 here, but the above one is the 8, the first packet. So that's 8 times that the AMS tried to end the connection. But the connection, if you see the start time, was 40:09, and then at 40:40, the FINAC finished retransmitting. So that's like 30 seconds of connection opened, and we don't know when it will finish. But on the firewall, these connections are not closed after 30 seconds. On the firewall, the setting for this orphan connections is 1 hour. So imagine having hundreds of thousands connections opened for 1 hour. Okay. Meaning, of course, the snot ports were not released, so no other outbound connections could be made. And let's see what happens with this data, right? The captures and the captures on the new infrastructure, the captures on the old infrastructure. We had the firewall team, which was able to provide us a fix. And basically saying, we applied a fix that will allow all the reset packets that are coming from the devices, from the cars, on the inside to be able to move to the outside of the interface. And this way, both sides of the firewall would clear the snot ports and release the connections. Let's take a look at some small numbers to understand a bit better the monitoring situation and how would you monitor this, because it's not the standard way you get in Prometheus or Grafana. So it took us about, I would say, 5 months, a bit more, and 50 people across 4 companies to figure this out. Like most people, we also use Prometheus and Grafana for monitoring different aspects of our infrastructure and services. And we thought our traffic was 2.5K. right? You have it in Grafana, you see it. Turns out that we had way more traffic that we didn't know about. Right, so we had an additional, like, if you take an example of 100,000 cars, each car would make a connection check about 2 times per minute. So you would have like 3.3K requests per second, which didn't show up in any metrics, right? But they did use CPU power, memory, and others in Nginx and in F5. So why didn't the connections make it onto the Grafana, right? Why they were HTTP requests in the end? So let's take a look at this. If we look at this like networking model, we can see that each request goes through different stages or different layers, all the ways to HTTPS. But if that request stops at the security layer, right, that doesn't count as an HTTP request yet. It didn't make it. So it will not be visible in Prometheus. It will not be visible in Grafana. So the only way to monitor these connections would be to monitor the failed TLS handshake connections, right? But this is a lower level than the application. So now a couple of key takeaways, I would say. Monitor everything, right? Besides the usual suspects, the primary metric, again, for identifying these kind of scenarios would be to monitor the failed TLS handshakes. How do you do that? That's, well, first you need to know. So you do a couple of TCP captures, and then probably you have Nginx logs or whatever other server you use logs. This metric doesn't provide an absolute number, but it is an indication if you have any failing TLS handshake connections. So also promote a culture of collaboration and empathy. So instead of assigning blame like, oh, we didn't do anything, it was you to change something, so it's your fault. Try to focus on constructive investigations that will actually help everybody and learn and evolve. And if you gain any insights, consider sharing these insights to raise awareness. But also, if you have any community that you're active in, make sure to also share that in the community. With this in mind, this blog post that you see here addresses network troubleshooting in an Azure Kubernetes cluster. It contains a bunch of scripts that we use to actually troubleshoot this issue. However, on our general TomTom engineering blog, you can find out more information about our business, life at TomTom, and how you can get involved as a potential TomTomer to solve complex technical challenges like this one. And also, for further discussions on this topic, or if you want to connect, feel free to reach out to me on LinkedIn. And that is it. Thank you.